Okay, so sorry about the small delay. It was a bit tricky to set up all the equipment after the holidays. So maybe what we can do is just to recap a little bit on what we were doing before the break, because I know it's been a while. So we were talking about the wave function, how this plays an important role for quantum mechanics, and let's see, okay, does this work? No. Okay. So the basic idea was that we're going to represent like a state of a quantum object using what we're going to call here the wave function. So this is not a completely sort of new concept, if you like, to represent something with a state. Even in classical physics, we've been doing things like representing the state of a ball that you might kick here by like position and velocity. But in quantum mechanics, what it'll turn out to be is that we represent the state using a vector like this. So this vector is sort of a little bit of an abstract thing, but basically any state is always represented by such a vector, and what these basis states here are like particular states, individual kind of distinct states of the physical system. So I gave you a couple of examples of what such states or like these definite states could be. So it could be like energy levels of an atom, or it could be like a particle goes left or right, or it could be a cat is dead or alive, or it could be even like the position of a ball. So maybe the position of the ball at the top is, let's just call that state 0, and then position of the ball at the bottom is state 1. Of course, we could have many more states. It's totally fine. And then generally, the state would be like, you put some coefficients on it, and then it could be actually any vector that's a superposition of both of those states. So what you can kind of already see from here is that the classical and quantum physics, so classical physics is sort of a particular case of quantum physics, because in classical physics, you're not allowed to have the ball sort of here and here at the same time. You could have it at the top, or you could have it at the bottom. You can't have it both at the same time. But quantum mechanics, that's allowed. So you can have something which is a little bit in the top or a little bit in the bottom, and then you can put like complex coefficients on these, so these are complex numbers. So these are sort of, you might describe it as being sort of in two states at once. So this is your classic kind of Schrodinger's cat kind of situation where, the cat is sort of either dead or alive, and then, have some combination. So some rules on these coefficients. So these numbers have to be normalized, and so that means that the sum of the absolute value squared or magnitude squared, so this is like these complex numbers, so it's like the norm of the complex number squared has to add to 1. And I think the last thing that we talked about right at the end of the lecture was how to write a general state of a qubit. And qubit is a two-level system, and this comes up a lot in things like quantum computing. So if you have a two-level system, so maybe it's like 2 levels of an atom or something, then you can put arbitrary complex coefficients in front of it, and these can be complex numbers, And so complex numbers have like a real and imaginary part. So basically kind of 2 degrees of freedom. So in a way there's like 4 degrees of freedom here, but we need them normalized, so that cuts it down to 3. And then I was arguing about something like if you have a global phase, that means basically if you have some e to the I theta term that just multiplies the whole thing, it never matters in quantum mechanics. So it's you can never really observe it. So it's kind of like a parameter that is there in the theory, but you can actually never really see it in terms of real experiments. So if you account for the fact that there's a global phase, so one of them, and then it doesn't matter what that is, so we can just set it to 0. E to the I 0 is 1, so you can sort of forget about it. And then you've got normalization, so that's like 2 constraints, or 2 degrees of freedom that are kind of removed. So 4 minus 2 is 2. So there's like 2 parameters, theta and phi, and basically that's the most general state of a qubit that you can run.
Professor, can you
Yep.
explain why it only has 2 degrees of freedom after the normalization?
Yeah, so well, I guess that's what I was just explaining now. So, I mean, so just to write it out for you. So alpha and beta, so this is actually sort of like alpha real, alpha imaginary, beta real, beta imaginary. So there's 4 degrees of freedom here, right? Basically 4 variables. Okay. And then we have this equation. So quantum mechanics says we've got to normalize our vectors. Okay. So that's sort of -1 because that's one constraint, so it needs to be that. And then there's a kind of a global phase. So this is not really a constraint actually, but the global phase, what that means is that basically like if I have the state, say I have the state, okay, alpha beta 1, and then, or if I have another state which is the same, but I just multiply it by e to the I theta. So this is a complex number, but it's just the phase part. Okay, so e to the I theta part. So this of course changes these coefficients here, right? So the alpha is now alpha e to the I theta and beta e to the I theta, and so not the same numbers as what this used to be. But actually, this is basically, I'll come back to this. Definitely, I will come back to this, I promise. You can never really see this phase. It's physically unobservable. And the kind of it's kind of hard to explain at this point, so I can't really give a really good explanation without probably launching into another 1 hour explanation. But let's come back to this point. But whenever you have like the 2 wave functions, and then they're basically the same up to this e to the I theta, it never really affects the result. So you could equally have this one or this one, and it would describe everything exactly the same. So it doesn't change anything about some any kind of physical results. So you could write it like this or like this, and it doesn't really change anything. Maybe the hint that I might give is that okay? What's a good hint? Okay, maybe the hint that I'll give is that say you measured this the probability of 0, okay? Then I think I told you before that the probability of 0 is actually alpha squared, alpha norm squared. So if I use this state here, then it's alpha squared. But if I use the bottom one, say I'll call that P0 dash, then it's alpha e to the I theta squared. Okay. Just because that's the coefficient of the 0, right? And then I'm going to modulus square it. But actually that's equal to alpha squared.
So the probability is the same.
Yeah,
so
the probability is exactly the same.
change.
Yeah, that's actually, it's sort of, it's not the full explanation, but that's a bit of a hint. Okay, so so basically this thing never does anything. You can't see it. You measure it. It gives exactly the same probabilities. So it is something which is not really relevant, or it doesn't matter what you choose there, is maybe the best way to say it. You could choose theta to be 0 or 5, pi, any number that you like, and it wouldn't change anything. So that's why basically, so it's kind of like -1 because it's irrelevant. Irrelevant. Okay. So it's there, but it's irrelevant. Okay. All right. So that means, so there's basically two degrees of freedom, which, according to how we parameterized it there, it's theta and phi. Okay, so that's the most general state that you can write for a qubit. In fact, this rule basically works for any number of states, even if I had like a 3-level system. Essentially, it would always be something like, say n was the number of levels that you had, right? Then there'll be two n complex numbers, two n degrees of freedom because of the complex numbers. Maybe I should say, yeah, just degrees of freedom. Degrees of freedom. But then kind of -1 for normalization, and -1 for global phase. And so there's basically always 2n minus 1 degrees of freedom. This is not part of the course. I wasn't going to include that, but well, this part. But this is always kind of true. Okay. Any questions? That's the last slide on this set. No? Okay. Okay, so let's move on to the next set. That was just sort of recap. So we're going to go on to a new topic, which is measurements. So we've talked about how quantum states are written in quantum mechanics, and now I'm going to talk about what happens when you measure it. And so measurement, it doesn't seem like a very sort of, you know, whenever you're talking about computers or anything like that, you never really think so much about measurement because you kind of take it for granted that, you know, you've got your zeros and ones on your computer stored on your, you know, flash drive. You kind of take it for granted that you can just read it off, right? It's nothing so mysterious about that process. But in quantum mechanics, actually, it's measurement is actually something that is kind of a little bit more active, that it actually does something to the state, and it's a little bit related to this thing that often gets thrown around, or saying that gets thrown around in quantum mechanics, that you can't look at something without kind of disturbing the state. So looking is kind of considered to be sort of the measurement, because it's got you involved. Presumably you wanted to find out something about the state, and then so you looked at it. But then basically as soon as you look at it, like in Schrodinger's cat, you do something to the state. So it's like it was kind of different to what it was before. So this is exactly kind of like your Schrodinger's cat paradox. So we're going to talk about how that all works here. Okay, so as we were actually just talking about right here, I said kind of as a rule that quantum mechanical states are always kind of normalized, right? So we always got this normalization condition. So why is that basically? Well, it's basically because ultimately when you're going to go and do your measurement, basically these things turn out according to the probability kind of relation, that the probability is the modulus squared of these coefficients. So you've got some quantum mechanical state like this, and if you go and say, okay, I'm going to put it in my measurement device, is it in the state 0, is it in the state 1, then what will happen is that it will kind of randomly turn out to be in the state 0, or it'll turn out randomly in the state 1, so with the probability of alpha squared or beta squared, modulus squared. So one thing to sort of keep in mind is, okay, so how does this kind of work in the lab? So this basically means is that when you put in your state, you can't really work out, say you give me some unknown state, right? So say you've prepared your state, you give it to me. So actually there's no way for me to work out what that state is with only if you just only give me one copy, because say you gave me this state alpha beta, right? So you chose some alpha beta numbers and then you give it to me. So then I go and measure it, and then let's say it was 0, okay? But just from one measurement, I can't tell what maybe alpha is was really big, that's why it was 0. Maybe alpha was really small. Maybe alpha was 0.1, and it's mostly beta. So the chance of me getting 0 was actually something like 0.01. But maybe I was just kind of unlucky, right? I just got kind of this really rare occurrence. Just from one copy of the state, I can't actually tell what these numbers are, because you need to kind of run this many times and then work out what the kind of statistics are, right? So, but before I explain that, suppose let's imagine that we've got our little device here, and we've got an electron that passes through the left and right sides, and because this is a quantum object, it can be in a superposition of going left or right. Yeah. And suppose that I kind of engineer this thing somehow so that it's always in this state of square root 3 I over 2, that's coefficient, and a half 1 there. So what is so maybe you guys can find the probabilities of being in the left and right channels.
So zero state is the left channel, right?
Yep. Yeah. Yeah.
3/4 is the first probability.
Yeah.
And
That's
then
right.
a quarter.
And a quarter. Yeah. So you prepared it in this quantum state, and basically what you'd actually see is that, you know, you'd send, say, 100 electrons, and 3/4 of them would be here. You'd find it here, and 1/4 you'd find it here. So basically, you run it 100 times, and 75 of them will be in the left, and then, you know, 25 will be in the right. So yep.
Wait, I have a question. So the probability of that, in both of them, so that's an OR, right? Like 75 times in the left and like 25 times in the one.
That's right. Yeah, it's or. Yeah.
That's an OR. So, but we are calculating, and what's the answer for and?
Not trying to understand what you're getting at. So, I mean, there isn't really an and because.
But we're asking of the probability in the left and right channel.
Oh, okay. Okay. I think you just. Yeah. Okay. Then it's just well, you know, that's just the phrasing of the question, I guess, right? So, I think the and here means find the probability in the left, and also find the probability in the right. So find it doesn't mean find the probability that it's in the left and right channels at the same time.
So what's
Yeah.
the oh.
Yeah. So it just means like maybe, you know, to be more explicit, I would say find the probability that is in part A in the left channel, part B in the right channel. That's all.
Oh, so,
Yeah.
so we just square the coefficient
Yep.
before. Okay.
Yeah, that's right. So you square, but yes. So modulus, you know, you got to do the modulus squared of this one so that the I disappears because the probability is always real. Okay. Yes. So this is sort of what I was kind of half explaining in the first slide. So, you know, what happens kind of in the lab is kind of a little bit random, right? So on paper, you go, fine, okay, I do the modulus squared of the number, get my probability, great. But if I'm doing it in the lab, this is what, you know, you do. So you run it, okay, so I said 100 here, I wrote 1,000. You run it 1,000 times, run the same experiment 1,000 times, and then you're counting how many times did it end up left, how many times in the right, right? And then so, you know, maybe some typical results might be, okay, I found it in the left one, you know, 753 times, and then, you know, 247 times in the right. And so you kind of estimate your probabilities to be something like this, 0.753, 247, and it's not going to be exactly the theoretical probability because it's a kind of a random thing, right? Like if you roll a die 1,000 times, okay, so theoretically 1/6 probability for each, but you know, it's not going to be exactly that, right? So it's going to be a little bit off, and then the more times you do it, the smaller the kind of error is, and then the more it approaches the theoretical result. So that's basically how it actually always works in quantum mechanics. You always have to run these things like a lot of times, and then finally you actually get these things, these probability estimates, and and then from there you kind of deduce what the these kind of amplitudes are. So also notice another thing that, okay, well, you know, what happened to this eye? It's not doing anything, right? So and that is also another kind of feature that for this particular measurement, this I does absolutely nothing actually. And even if this was a minus sign, or even some e to the I theta floating around here, you would actually not be able to sort of see it in the probabilities. You get exactly the same kind of numbers, right? Then you might ask, like, okay, so why do I have the I in the first place? It's not doing anything. So the answer is, and we'll do this in the next probably few lectures, is that actually this is not the only measurement that you can do. So you can actually do measurements that are not just 0 or 1. This seems to be like the most obvious thing to do over here. But actually you can do other types of measurements where you actually do see the effects of, say, this I or a minus sign or something like that. And then it actually does matter that those are there. And so when you do like a quantum mechanical measurement, actually it's not like there's only one type of measurement. There's actually many types of measurements that you could do. And for this one, the I and the signs, it just doesn't matter. It doesn't even show up. But for other types of measurements, it will. So, okay. Right. So let's kind of maybe look at this sort of a little bit more sort of abstractly or more mathematically. So let's think of like what actually happens to the state of the system. So, you know, what I've told you is that, okay, you measure the qubit and then you get these probabilities. But what's happening to the actual state? So maybe we can picture it like this. So we have that initial state here. We sort of shove it into our measurement box, right? So this is some huge device. You know, huge. By huge, I mean I'm kind of picturing, you know, that this quantum object is probably like an atom or something, and in comparison to the atom, it's going into this enormous kind of machine that is, you know, human sized, right? So it's enormous compared to like an atom or something. And basically what kind of that does is that it sort of changes the nature of the state. So it randomly, after it goes into the measurement device, it you know, you measure 0, and what measuring 0 means is that actually now the state really is in the state 0. Okay? So you get that probability, but the state is now actually physically in the state 0. And likewise for the other result, state actually is in the state 1. So the state of the system actually gets changed. So it's no longer this alpha 0 plus beta 1 state. It's now changed into 0, 1. Okay, so it makes sense. So then, so what happens if I do another measurement after that? Okay, so suppose I did my measurement, say it turned into the state 0. Suppose I go and measure that again. I can just, you know, loop it back into the same machine and then measure it again. Then what happens is, as you would expect, well, the state is 0, right? So with probability 1, you actually get the state 0 because it's in the state 0. Okay, I'm saying something kind of obvious, but you know, after you measure it, if you see that it's in the state 0, it actually is in the state 0, and the state is no longer the thing that you started with. And then thereafter, if you go and measure it, it will always be in the state 0, no matter how many times you go and measure it again.
So, to bring back to the cat analogy, does that mean if I open the box and the cat is dead, it won't be alive again?
Yeah, yes.
And if it's alive, it will never die?
Well, yes, kind of yes. If you take the example to the extreme, yeah. 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 So it's really only this first step, that first measurement, that changes things. And basically, after it's in these states of 0 or 1, it's kind of back to your regular kind of classical state. So remember in the last set of slides, I was saying that, classically you can only have 0 or 1, and in quantum you can have like a superposition, you can have it both. So basically what's happened is that after you measure it, it's turned into this kind of classical state, right? And once it's classical, just like your zeros and ones on your computer flash drive, it really is in the state 0. So you see it in 0, and then you go and have a cup of tea, come back, it's still in the state 0, as long as nobody's touched it or something. So this is what you call kind of the collapse of the wave function. Sometimes you hear this kind of terminology that somehow it was in this quantum state, and you did your measurement, and then the state kind of collapses. So it collapses into this kind of classical state of either 0 or 1. Yeah.
Can you take us through what exactly happened when it collapsed, and like what kind of measurement is implicated? Is implemented, so is it like as long as I measures it, by any means it will collapse?
Yeah. So yes, I mean this is sort of I've kind of written it more abstractly here, but if we go back to our example here, then before you go and measure it, I didn't really draw any measurement devices in this picture here, but presumably there's some probes here that are checking whether it's in this state or that state, right? And so in this case, the probes to check is it left or right. That's our measurement device. But that's just kind of one example. It sort of turns out any measurement, so regardless of kind of the experiment that you're doing, so this is some experiment in probably semiconductors and stuff, right? But even if you did it with like light, so if you send some photons through a beam splitter, trying to measure where the photon went, you're doing something with superconductors or ions or atoms, basically it always reduces to this kind of scenario that you try and figure out, is the state, here or here. Doesn't matter like what kind of devices that you're using, what kind of physical system. You'd be using really very different types of experiments, but it always kind of reduces to this. So that's why we can sort of abstractify the whole kind of process and say that, well, basically every time you do anything like this, it kind of turns into that. Did that answer your question?
Yes.
Okay.
That sounds weird.
Yeah, I guess it does sound weird. It's true. I would also expect that, if you're doing something with photons, it'd be kind of slightly different to if you're doing something with, electrons or something like that. So, but I guess that, there's a sort of a common thing that you're trying to achieve, right? So despite the different physical objects that you're dealing with, the question that you're trying to answer is, is it this one or is it that one, right? And then because kind of the question that you're asking is kind of the same in all these, that's probably why it reduces to the same thing. Might be one way to think of it. Okay. Right, so let's get a little bit more mathematical. So how do we sort of formalize this kind of measurement process? So what we can do is we can define these things called measurement operators, and so this is the first time that we're going to deal with an operator. Right? And remember in our kind of linear algebra primer that operators always looked something like, well, you know, an operator, so if you have some operator T, then basically, you know, this was represented as some kind of matrix, right? And if we decompose that matrix, I think I wrote a form of the matrix, so if I and J are matrix elements, then our matrices, you know, you can write our operator as some kind of outer product of the vector and its conjugate vector, because I think I explained that, you know, such a combination, basically the role of it is to turn a vector into another vector, transforms one vector, and in general turns it into some other vector. So psi turns into phi. So because we're dealing with some process where we're starting with some vector, that's our state, right? I'm going to measure it, and then I've said that after you measure it, the state changes, it turns into something else. Yeah? So this means that we should use operators to denote that kind of change, because, you know, state is going to change. So it turns out that measurement operators are pretty simple. So we can define a measurement operator for each different outcome of the measurement. So say this outcome where, okay, so it's in state 0 or it's in state 1. So each one of those different outcomes is associated with a different measurement operator. And then what we can do is we can work out what the probability of a particular outcome is by using this formula. So it's n multiplied by the state, and then that state, complex conjugate, that turns into a number. And also the new state after the measurement is given by this. So it's basically n, you know, whatever the outcome is, times the state. And then actually, if you do this, the state is actually not normalized. So in order to normalize it again, you need to divide by this factor of square root of p, which is actually just defined there. And that's our new state. Okay. So let's see. So probably seeing the general formulas, you don't really, it's hard to sort of understand it. So I've just written everything out for the simplest kind of case here. So say we're going to start in this qubit state. So there's a lot of equations here, but actually it's all pretty simple. So say we have this state, that's what we're starting with. And remember that basically what happens is that you do a measurement and then either becomes 0 or 1, and then the probabilities are like modulus of a squared or modulus of b squared. So that's what's supposed to happen. So let's see if the mathematical machinery is going to give the right result. Okay, so let's look at the 0 case first. So consider the case that it collapses to this state 0. Okay, in that case, so we're supposed to use this measurement operator. And in this case, the measurement operator will be like 0 ket, 0 bravo. Okay, then the probability is, that's just the definition of the probability. That's just the formula that I had. But I put some brackets around here just to emphasize that actually it looks like you have to do this long vector matrix multiplication. But actually what it is it's just like you multiply m to the state, okay? And then this is just a complex conjugate the complex transpose of this thing. Okay, because if you do, so m times state, if you take complex transpose, then this is equal to this. Basically, kind of because if you know your rules about transposes, it's so this is our state. This is our state psi. Okay, this is our matrix M, and Hermitian conjugate is actually taking the complex conjugate and then doing the transpose, right? So basically, this is going to be, okay, so psi 1 star, psi 2 star, star, psi n star, transpose, and this is going to be like m1 star, m12 star, transpose. So that's basically what that is. Okay, and then when you do, I should do, we have to do the transpose on the outside. And when you have transposes, you actually reverse the order, if you remember. So it's going to be this, psi 1 star, psi n star, and then it's going to be this thing transposed. So it's going to be m11 star, m21 star. Right? This is 2 1, this is 1 2. So this is being transposed, this is being also transposed, right? So when you do the complex transpose of all this, it's actually just the same as this, and then the probability was psi m dagger m psi. So actually, you just need to work out what this thing here is. That's some vector, and then you just take the complex transpose of that. So whatever this thing here is, so we can work out what that is. Say let's call that phi. So this is actually just always equal to phi. Okay, I don't know if I confused you. Okay, let's just keep on going with the example. Maybe will be clear. So what I'm going to do is first work out what m times the state here is. Okay, so that's 0 0, and then that's that state. And basically what we do is we just multiply out this the inner products. So 0 inner product with 0 is 1. And 0 inner product with 1 is 0. So that just disappears, and you just get a of 0. Okay? And then to work out the probability, basically that's this part, a of 0. And then this is what I was trying to argue there, is that this bit is just the complex conjugate transpose of this, right? So that stuff, it's always the complex conjugate transpose of that. So it's just going to be a star, and then the transpose of this 0. So it's a star 0 times star, that's what we just worked out. And so that's, and then this inner product is 1. So it's a star times alpha star times alpha, and that's just alpha mod squared. Okay. So that recovers our result from before. The measured state, we just worked out what that was, and I've said you've got to divide by the probability square root. So just plug those in there. So it's alpha state 0 divided by probability root. So it's actually alpha times 0 divided by alpha mod. So okay, so that actually leaves some complex phase. Actually, this complex phase we don't really care about. It's this global phase that doesn't do anything. So often I don't even write it. So the steps are, I think, kind of straightforward. For the one case, it's just the same, except that you get beta instead of alpha here. So of course the probability will be squared, and you get this beta over beta mod. It's 1. Okay. Okay, so if you did it like that, then you could also do it with matrix notation. Basically the same thing. So we can write actually our measurement operator like this. So our measurement operator was like 0, 0, and actually that corresponds to this matrix, because that's 0, and this is one state. So this is the element for 0, 0. Okay, so we can just multiply this m with our state. It's our state. Just matrix multiplication, we get alpha 0. And then we can work out our probabilities by just, again, this part is just complex conjugate transpose of whatever we just got here. Yeah? So then you just lay it on its, lay it down, take complex conjugates, that's alpha star 0, alpha 0, just do the matrix multiplication, and it's alpha squared, as we had before. And over here, we again just take that, whatever we had there, divide it by the square root of this guy, so then it's alpha divided by mod alpha, and it's 1, 0. 1, 0 is state 0. Okay, so it looks a little bit sort of convoluted, but it sort of formalizes everything. Basically, it's always this. It always gives the same thing as this stuff here. But what it does do is that it means that when we come across like more complicated measurements, we can actually handle it kind of a little bit more easily. For this case, it's a little bit overkill, as you can see. It's like doing a page of calculations just to get something you can just see in like 1 second. Yeah, so it sort of helps to formalize things for later. Okay, makes sense? Okay. Yeah, okay. All right, so I think, okay, as a final, maybe, or yet another example, remember I was saying, like, if you do a measurement, okay, so it collapses to 0 or 1, but then if you do another measurement after that, then it will be in this state 100% of the time. So what this slide is just doing is to just verify that. Okay, so in this case, at this point, the state is supposed to be in 0, yeah? So it's 0. Then suppose we measure the 0 outcome. So that means we multiply n0 by the state. So that means it's going to be, 0, 0, that's our state, that's our measurement operator. And this thing is the answer that I got from 2 slides ago, this one. Okay, so just plug that in there, so that's that. The probability of that is, just put that into there. This phase cancels out, so it's just 1. And here, to find what the state is after this measurement, so what is that one? Then I just put that guy into the formula, divided by the square root of 1, just 1, so we get the same state. For the one case, so remember this was going to happen with probability 1, so 100% of the time it's going to be 0. But just, to see what happens for the other case. Alright, so I'm going to multiply measurement operator 1 with this state. So it's going to be, that's our measurement operator 1, multiplying it by this. So, that phase. 1 and 0 are orthogonals, the inner product is 0, so that factor gives 0, and that's just 0. So it's, zero vector technically, but it's zero. Probability is zero because it's a zero length vector, and then the state is, well, it's got amplitude zero, so it's zero. Okay. Right. So we've already talked about this, but this, you know, this phase is something that never really kind of matters, because it's a kind of unobservable, and you could sort of see this, for example, in the second measurement. So remember over here, when I measured the probability of this one, even though there was this phase lurking about, actually the probability is just 1, and this phase doesn't ever matter. As I was saying before, even if you have any kind of complex phase, anything from the unit circle, it doesn't affect the final result. So all these states here are actually physically equivalent. So even the minus sign I, or even 1 minus I over root 2, you know, these are all just phases, and so these are all actually, from a physics standpoint, completely equivalent. Okay, so let's just maybe get a bit of practice with this. So let's just basically do the same example that I had a couple of slides ago, but let's this time use the measurement operators. Okay. So I think you might need a pen and paper for this, or an iPad. You can just start with this state, and then firstly find the probability so it's in the left and the right channels, and then also find the wave function. Let me write the formula up there for you. So the formula for the probability is that, and then the formula for the measured state is that. Okay. And then the measurement operators that we're dealing with, so M0 is, so these are the two cases. Yep.
How do we calculate M0 again? Zero,
I guess you don't calculate it. I mean, I've given it to you here already. So
is that a matrix?
that is the matrix, yes.
Is that a 2 by 2?
It is 2 by 2.
How to determine?
So if you prefer the matrix method, then you can look here. But maybe I can say like how you work this out to be how to work out the matrix. So, you know, in a matrix you always have to have some convention, right? So so if you have the convention that this is like 0 and 1, this is 0 and 1, then, well, okay, maybe I should write it sort of like this. Yeah. So then basically this is the element for 0, 0K, 0 bra, right? And then the fact that there are no other elements here, I mean, basically implicitly this is like 0 times the other elements, right? 0, 0, 1, 1. But because it's all 0, you don't bother to write it, right? The coefficients of all these are 0. So that's basically, yeah. So when you convert this to matrix notation, you would basically just put a 1 here because that's the coefficient of this term here, right? And then likewise when you write the state, because a state that we're dealing with is root 3 I over 2 plus a half 1, right? So again, you have to follow the same convention, the same ordering of the elements, of course. So because when you write a vector, it's 2 by 2 vector, and so you have the same ordering convention, and then you put in the elements in that convention. And then so you could do this one by matrix multiplication, a bit like how I did it over here. But I think it's also useful to also do it just directly in this bracket notation, because in that case you sort of work it out a little bit differently. Basically what you're always doing is that you are kind of using these orthogonality properties, right? So like for example here, we've got this n here, we've got the state, and basically what you're doing is you're going up. This is a bra and this is a ket. Take the inner product of these one, that's 1. Take the inner product of this one and this one, that's 0. So this 0, this 0, inner product just becomes 1. So that's why this is alpha times 0, and that's that ket. Both are equivalent, but you can use which one you prefer. I think I actually prefer this one. So, Elin, how's it going? Finished? Yeah. Okay, so let's see. Alright. Okay. Yeah. Alright, yep. Okay, good. Alright, that looks all correct. Okay. And you're doing the matrix method.
Yeah.
Okay. All right. Yeah. So I think in the end, like the matrix method, you might be more familiar with it, but it's also good to get accustomed to this bracket way of doing things too. So, okay. Let's see. Okay. So that's actually the end of that. Okay. Any questions for this set? Alright, okay. Well, we can make a quick start on the next one. Okay, so next we talk a bit about basis rotations. So this sounds a little bit sort of abstract, but it kind of connects also a little bit to what we were discussing before about the fact that when you did those measurements in the last set, the complex I, it seemed to do nothing, right? So, why have those factors? And basically the answer is sort of coming in this set, right? So, basically those factors do come in different types of measurements when you, and they're more apparent when you rotate to different bases, okay? But let's start at the beginning. So, if we forget about sort of quantum mechanics for a bit, and let's just think about another kind of vector space, which is, say, velocity. So, if you've got a plane flying in the air, like this, so we've got this plane flying this way. Now, of course, just depending on your perspective, so we've got Alice, Bob here, looking at the plane and, standing on a field somewhere looking up at this plane. And of course, which way they're facing totally changes their relative perception of which way this plane is going. For example, for Alice, looks like the plane is going over the top of her head, towards the back of her, but of course for Bob it's going sort of in the forward direction, right? So, we can view this as them having different relative kind of coordinates. So, Alice and Bob, their kind of center of reference is, of course, where their head is. And so, in terms of those coordinate systems, this vector will apparently look different, right? So quantum mechanics is actually the same. So when we said that general quantum state can be written in terms of a set of physically distinct states, so we said, 0, 1 to n, and n things were like physically different states of the system, like energy levels, or the electron is left, right, the cat is alive, or it's dead. So these are, physically distinct states. But actually, another way to sort of think of that is that these are actually some kind of basis vectors to describe the quantum system, right? So we can kind of picture this 0 to n as being actually just some kind of, coordinate system, a bit like, Alice's coordinate system that we had here. This was, of course, the velocity, but in a kind of an abstract sense, we can view this as just one particular kind of choice of how to represent the quantum state. Right? And we didn't have to choose that set of states. We didn't have to choose the electron as sort of left or right, cat is alive or dead. We could have chosen another one, but we just chose that one. Right? So what we could do is we could choose a totally different set of basis vectors. So instead of the 0 to n that we had before, we could have chosen maybe just some other set, a bit like Bob, but it's a different kind of reference frame, if you like. And we could write exactly the same state. So this is totally, exactly the same side, right? But this time it looks different just because you're going to represent it differently. Just like because Bob is just looking in a different direction to Alice, so it just looks different. So in the same way, this state kind of has different coefficients here. So the V coefficients are going to be totally different to the A coefficients. But it physically is exactly the same vector because we're just using a different set of basis states. And just like with the original set of basis states here, these things should also be kind of orthogonal. So the n and m, they're kind of right angles to each other, you can imagine. So if you choose the same basis states, then the inner product of those two will be 1. But if you choose two different ones, then they'll be orthogonal. So it'll be 0.
Is this something similar to adding a general phase into the previous state?
You mean like, are these B's, is it sort of like adding a phase to the whole thing? I'd say kind of no, actually, because it's actually kind of much more different than that. Okay, so how about we just look at this example here, and this might sort of give you a better feeling for what I'm trying to say here. So suppose we had this qubit state, right? This is the thing that we've been dealing with. So just qubit, 0 and 1, some coefficients, alpha and beta. Okay. So that's one way of writing state, but I could have actually chosen another set of states, and often these states are called plus and minus. You can kind of picture these states. So this is like 0 plus 1 over 1 over root 2, 0 minus 1, 1 over root 2. So you can kind of picture these states as being sort of kind of in between the 0 and 1 state, right? So we've got our 0 and 1 state, they're perpendicular. And this plus state is sort of 45 degrees to both these. And the minus 1 has got a minus sign here on the 1, so it's kind of 45 degrees down. And this big blue vector here is the state that we're trying to represent. So, so this state, of course, will have actually completely different coefficients depending on if you choose 0, 1 or the plus minus basis. So if you imagine this as your sort of axes, of course, the coefficients are totally different. So it's not even just like a phase or anything like that. I mean, they're totally different numbers. Right? And yeah. Okay. So maybe we'll talk about this more next lecture. But these basis vectors, the plus or minus, these are also orthogonal. So that's why I've got this 1 over root 2 here, so that when you take the inner product with itself, it has a length of 1, also for the minus, of course. And if you take the overlap of these two, then this will be 0. Yeah, I think I don't have enough time to fully explain this one, but basically, maybe we'll go through the calculation next lecture. But as you can see here, what you can do is rewrite this state in terms of this plus and minus, and it will turn out that the new coefficients are something like alpha plus beta over root 2, alpha minus beta over root 2. So, of course, these can be radically different numbers to the original ones. Okay, all right, maybe we'll leave it there for this week, and see you next Thursday.
So Professor, is this rotation like just times e to the power of I theta to the wave function?
Yeah, so I would say it's like more than that, because I think there's no.
Different. It's different.
Yeah, it's more than that. It's like you couldn't get these coefficients alpha plus beta, alpha minus beta, just by multiplying it with a phase.
Oh, so it's kind of different.
Yeah,